What I'd like to do now is move on to the question of reverse causality. So what I've talked about is when your problem is confounding, that you think there is something else that's correlated with the treatment that you're interested in that's really causing the effect, and we want to rule that out. Reverse causality is happening whenever we think that the outcome is affecting our treatment. So if we're thinking about income to health, it could be that people with higher income get better health care, better nutrition, and get better health. It could also be that people with better health can earn more money. So we have two-way causality. And so what we want to do is try to figure out some way of identifying the effect of income on health and not the effect of health and income. So we want to see 1 hour of causality at a time. And that's very difficult to do. And there have been two approaches developed in the literature to do this. And one is the timing of social determinants changes relative to the timing of health changes. So the idea of this approach is really that timing is related to causality. That things that happen first cause the things that happen later. And it's not that the future is causing the past, it's that the past is causing the future. And by looking at the timing of things, we can see what the causal effects are. This approach definitely needs panel data. Cross-sectional data is not going to be sufficient because in a cross-section, all at the same point in time, we don't see this temporal ordering. However, when we have panel data, when we interview or survey the same people over time, we can see what's happening in time, and we can see changes in social determinants, we can see changes in health, and we can examine which comes first. There's been very good work by Anne Case on this using panel data. And what she finds is that the social determinants of your parents seem to have very big effects on the health of children. So the health of children is very highly related to the prior socioeconomic status of your parents. And then that health as children goes on and affects your income and socioeconomic status as an adult. And so it's your health and education as children that are determined by your parents' socioeconomic status. And then those health and education that you have affects your own socioeconomic status as an adult. And because she's able to look at a very long run of data intergenerationally, she's able to look at these patterns. And what she sees very clearly for adults is that the health shocks tend to come before the income shocks. So in adults, we see these health shocks, that health changes. We also see income shocks, but it's the health shocks that tend to come first. So people get sick and then they become poor. It's much less common that someone becomes poor and that causes them to get sick. It's more the other way around. So this type of timing effect in panel data, I think, gives us some idea of causality. I think there's one caveat to this, there's one worry, that usually we believe that the timing proves causality, but there's a counterexample. And the counterexample is expectations. The problem with expectations is that behavior today may be a function of what you expect to happen in the future. So the future may actually affect the present. And an example of this in the literature is the effect of education on HIV/AIDS. So in the HIV/AIDS literature, there's a large literature on the effect of education on HIV/AIDS. The education tends to come first. People tend to get educated when they are young. They tend to become infected with HIV as young adults. And the idea is that the education is affecting their whether or not they acquire HIV/AIDS. So education may affect behavior, and the behavior affects the incidence of HIV and AIDS. And those papers assume the causality runs from education to HIV. There's now a small number of papers in the literature arguing that what we're seeing in some South and East African countries today is reductions in education because people are expecting that they may acquire HIV/AIDS. So they become fatalistic. In a high HIV/AIDS environment, they feel that there's a high chance they acquire HIV and that there's not much point investing in education or doing anything for the future because it doesn't matter very much. And if that's the case, then we get this reverse causality even across time. That it's not that these low education people are getting HIV/AIDS because they're low educated, but the prospect of acquiring HIV/AIDS has caused them to get low levels of education. So the expectation effect probably isn't that important most of the time, but in some cases, it may undermine the causality argument based entirely on timing. So you have to be a little bit careful with using timing. But I think in general, the timing arguments are quite convincing. Another approach used a lot by economists to try to overcome reverse causality is an instrumental variable. And for an instrumental variable, we need an instrument that is correlated with the treatment, but that does not affect the outcome directly, nor is it correlated with any other factor that affects outcomes. So these instruments are incredibly difficult to find. So an example of a very good instrument for income would be winning the lottery. If you win the lottery, it is like a random assignment of income. That would be an instrument. People who win the lottery get richer, and we can think of that as something that affects income, but does not directly affect health. And it's uncorrelated with any other factor because it's random. Usually, however, these instruments are less convincing. So the instruments for socioeconomic status may be things like distance to school. So people far away from a school, they're less likely to get education. And then we look at the effect of education on health using distance to school. But distance to school may have other effects. It may be that the school is in a local town, and so you're also measuring distance to health centers. And so it may be that you're really picking up the effect of distance to health centers on health, not the effect of distance to schools. So I think the instrumental variable approach is only as good as the instrument that you use. And it's very, very difficult to get convincing instruments. I think most of the instruments being used in the literature are not terribly convincing. The data that we have is often selected. We don't have the full data set. We don't observe everything that we would like to observe. And this may cause biases in our model. And there are two approaches to addressing this, this bias. The first, the simplest approach is inverse probability weighting. And this is actually a common approach in all survey samples. In a survey sample, you sample the population, but not everyone is equally likely to be in the sample. And so some people are more likely to be in the sample and some people are underrepresented. And so what we do is weight the sample so that people who are underrepresented, those type of people get a higher weight. And so in the final analysis, they're weighted more heavily. So in a sense, if, for example, old people are underrepresented in a sample, we will weight old people more heavily in our analysis. Perhaps each old person will count for 2 people, and that will rebalance the sample so that it reflects the population. That approach can also be used if people are missing for other reasons. That's the reason when the survey design actually excludes people by the design of the survey, or undersamples some people. If people are missing for some other reasons, for example, people who are people may be working away from home, they may not be sampled, or some people may refuse to answer questions, and so we don't have information about them. We can use this same approach by basically giving more weight to similar people who do answer the question, and letting those people stand in for the ones who are missing. Another approach is the Heckman selection model, which is a better approach if the selection is really important and is going on for some reason that may really be biasing your results. And the Heckman selection approach is to explicitly model selection into the sample. So we'll have an equation which is, say, education affects health. And then we'll say we only observe the education and health of some people. And we're actually going to have a model of that. We're going to model why some people do not come into our sample or why they refuse to answer the questions. And then we jointly estimate the selection and the outcome model of interest. That's a much more complex approach. I would say that the area in which I think this is very important is in HIV/AIDS. So in models that involve HIV/AIDS, people often refuse to answer. And so in some surveys, you get 20 to 30% refusal rates to answer questions about HIV/AIDS or to give a blood sample. And in some surveys, it's actually 50%. Half the people are refusing to answer questions or to give blood samples. And so we do the analysis. We're only doing the analysis on people who agree to test and answer the questions. And that may be very problematic if the people who refuse to test are different in a systematic way. We may not be getting a correct view of the population. And that may be particularly the case of people who suspect that they're HIV positive may be less likely to test. And we have some evidence of that HIV positive people tend not to want to participate in these sorts of surveys. People who know they're HIV positive are suspected. So in those cases, you might very well want to think a lot about selection into the sample and actually modeling the selection process and thinking about why people are not participating and then modeling that to adjust the final estimates. So I'll just point to that as a problem for which there is a solution technique, but it does require this quite complex modeling. So up until now, I've been talking about what are essentially statistical fixes. And the statistical fixes are we have this observational data that has all these problems. And what we're going to do is be very clever and come up with a statistical method of fixing the problem. However, another approach is to say, well, that observational data is very difficult to work with. What we can do is an experiment, and that experiment will give us a treatment and control group, and we can just compare the results. And we don't need to do sophisticated statistical analysis. And so the experimental approach, I think, is really promising as a way of solving all our problems and minimizing on statistical analysis. With a well-designed experiment, with a treatment group and a control group, the only difference that we are interested in is the difference between the treatment and control groups. We just need to see the average outcome for the treated guys, the average outcome for the controls, and we look at the difference. The treatment effect is the difference between the treated and controlled. It's incredibly easy. So the experimental approach, I think, is a very promising one. And I think in a lot of this area, it's becoming more common. I'll talk in a moment about randomized controlled trials, which are actual well-designed experiments that solve all our problems. Well, or solve most of them. Actually, we'll see that there are still a few issues to be addressed. If you don't have a randomized controlled trial, we can still see the results of natural experiments. And what a natural experiment is, it's something that is like a randomized controlled trial, but without the randomization. It's a social policy that has treatment and control groups. So this social policy gives us treatment and control groups, and we can compare the different outcomes for these two groups. The standard estimator here is a difference in difference estimator, and essentially it's the effect over time in the treatment group. So basically what we do is look at the effect of the treatment group before and after they got treatment. So we can think of the treatment effect as what the group was like before they got treatment versus what is like after they got treatment. So the treatment might be giving them an old age pension, it might be giving children a child support grant, it might be doing something on education. And so over time, the treated group is different than it was before. We also have a control group who don't get the treatment, and we look at the same effect over time in the control group. What happened over time in the control group? And what we do is a difference in difference. We look at the outcome in the treated group over time, the change over time, minus the change in the control group. And what we're really doing here is saying there was an effect of over time in the treatment group, and the counterfactual is what would have happened if they didn't get the treatment. And what we think would have happened is they would have evolved like the control group. So what would have happened is the treatment group would have got the same outcome as the control group over time had they not been treated. So the counterfactual is the control group. And we're looking at changes over time and comparing between the two groups. And these natural experiments, I think, are quite convincing if the control group is very like the treatment group. So you can plausibly argue it's a good counterfactual. So it has to be that the control group is very similar to the treatment group, and you can argue convincingly that the outcome would have been the same in the treatment group as the control group. This is some work that I've done myself in the MATLAB in Bangladesh. And this is joint work with Omar Rajak. And what we did is look at the effect of measles vaccination on schooling. So this actually goes the other way from the social determinants literature, which would tend to look at schooling on health. This actually looks at health on schooling. But it's an example of this sort of natural experiment. What happened in MATLAB is where MATLAB was divided into 5 areas, 5 blocks. And the measles vaccination program was rolled out separately in different blocks. So in 1981, the program was started in blocks A and C, and then it went on over time. And in 1984, it started in blocks B and D, actually towards the end of 1984. Very near the end of the year. And in block E, it didn't get rolled out until 1989, after our sample. And so what we have are children in these different blocks get different measles vaccination rates. So what we see in block A is the measles vaccination rate in 1980 is 0, and the age-appropriate measles vaccination rate in 1981 is 37%. And then it goes up gradually over time. The same happens in block C, and in blocks B and D, the rate goes up from the end of 1984. A few children get vaccinated at the end of 84, but then the rate shoots up at 85 onwards. And we always have a very low rate in block E. And what we can do is compare outcome for children who were in different blocks at different times, and basically say the children in block A in 1981 and 82 are very similar to the children in block B, except that the children in block A got measles vaccine or are more likely to get it than those in block B. So that this is essentially like an experiment where some people get the vaccine and some people don't. And so I think it's pretty convincing that this works, provided these different blocks, B and D and E, are adequate controls. So there is a worry that other things were happening at the same time in blocks A and C that would confound this. If other interventions are happening, and actually other interventions were going on. And so it's not as convincing as it might be. And actually, if you look at the paper, what you see is that there were also family planning interventions, there were iron supplementation interventions going on, not at exactly the same times, but in different blocks at different times. And so we have to control for those. But this design of having an intervention and control group, I think, gets us close to a randomized trial and gives us convincing evidence. Also in MATLAB in Bangladesh, there was a intervention which was a family planning intervention. And this is the effect of that family planning intervention on fertility rates. And so what this shows is the fertility levels of women of different ages in 1996. And the family planning intervention started around 1979. And what you see is that old women, those over 55, had completed their reproductive life before the intervention happened and are not affected. Fertility gap tends to open up over time for women as they have more children. And in the older age groups, there's a difference between the treatment area and the control area. So some areas of MATLAB got the family planning intervention and some didn't. And so if we believe that the treatment area would have evolved like the control area if it didn't have the intervention, this is the causal effect of the intervention. So the important point here is having a control area as well as a treatment area. If we just have a treatment area, we would see that fertility goes down over time, but fertility is going down over time everywhere. We need a control area to compare with to see what's happening in the control area at the same time. Another very similar example is a family planning intervention in Navrongo in Ghana. This intervention happened much later. And these are the observed fertility rates in 1995 and 2001. So in 1995 is before the intervention, and in 2001 is after the intervention. And in the treatment area, we see the age-specific fertility rates for women in the prime reproductive ages has come down. In the comparison area, not much happened over time. Now, if we just had the treatment area, we would say there's been a reduction in fertility, but other things could be happening over time. The fact that in the comparison area, over the same time, not much happened, leads us to conclude that it's probably the treatment that is having this effect. So we really need this comparison area in order to rule out that it's just a time trend that we're seeing, that fertility is just going down over time anyway. So I think this is pretty convincing evidence that the treatment worked. That family planning intervention was also linked to a child's health intervention, which had an effect on children's mortality. And again, we see significant effects in the treatment versus control areas. So this approach allows us to estimate intervention effects, the effects particularly of policy changes. Intervention effects tend to be at a point in time, though. And the problem is that the changes that we see after an intervention or a policy change may simply reflect time trends and reflect other things that are happening over time in the same place. And so, to get convincing results, we usually use regional variation in pre-intervention prevalence or some other factors to construct region-specific effects. So what we need is regional variation. We need some areas to get the intervention and some areas not to get the intervention. So we can compare treatment and control areas. Without that, we're really not sure whether it's just a time trend effect. And then we can measure outcomes in terms of mortality, health, education, and income. A really important point that has recently come out of this literature is that the significance tests need to be adjusted for correlation because treatment is at the group, not individual level. And what I mean by this is, if we look at these interventions, they tend to affect some groups, not other groups. But there may be thousands, sometimes tens of thousands of people in each group. And if we just run the regression, then what we tend to get is very high levels of significance because we have thousands of observations. But the treatment is on one group rather than another. And so the number of observations we have is actually more similar to the number of groups that we have rather than the number of individuals. And the problem is individuals within a group may be correlated. They're not independent observations. If we had 10,000 people and we randomly assigned them to treatment and control, we'd have 5,000 treatment and 5,000 control. But if the people live in different regions and we pick one region for intervention and one for a control, we really only have one treatment group and one control group. And the people who live in the same region may be similar in many ways. They may interact with each other. And they don't give you as much information than if you had individual randomization. And so there is a literature now saying we have to adjust our standard errors for treatment at the group level, and we tend to get less significance. Some things may not be significant when we do this adjustment. So this is a technical issue around significance for group level interventions. And we'll see that when we come to the homework. So homework 2 will look at this issue. And one of the things we'll look at homework 2 is correcting for the fact that interventions at the group rather than individual level. I'd like to finish up by looking at what I think are the best quality data. And the best quality data come from randomized controlled trials. And the great thing about these randomized controlled trials is that they really have the potential to overcome all of the problems that I started with. They will overcome confounding in large samples. The treatment is randomly allocated to people. In a small sample, it may be that the treated guys are different from the control guys just by chance. The people who get the treatment may actually be very different from the controls. However, as the sample gets large, that becomes increasingly unlikely. In a large sample, it's highly unlikely that the treated and control groups are different. And that means that the counterfactual argument becomes strong in a large sample. The treated group is just like the control group, except it has the treatment. In small samples, if you only had 2 people saying one got the treatment and one didn't, it wouldn't be very convincing because the guy who got it is probably different from the control. But as the samples get very large, the treated and control groups become very similar, except by the remotest of chances. It overcomes reverse causality. It can't be the outcome is affecting the treatment because the treatment is randomly allocated. So we don't have a reverse causality problem. It overcomes selection if there is no loss to follow-up. So if you do an experiment, you give some people a randomized intervention that affects some social determinant, and then we go to measure their health. Some people may not be there when you go to measure their health. You lose them to follow-up. And that may be a problem if there are a lot of these people. This may be a selection effect that will bias your sample. And the worst possible selection effect is loss of follow-up due to death. So if the health outcome, you want to measure the health of these people after they got the intervention. If these people die, it's very important that we know that they died, and that's a very bad health outcome. If we simply don't know what happened to them and they're counted as lost to follow-up, it may look like the intervention is very good because we're not counting the dead. So the selection problem comes in again here if we don't follow up everybody. So in an experiment, we have to make a big effort to follow everybody up so that we don't get this selection bias, that people with bad outcomes somehow get selected out of our sample. We do have the power effect, and it may need large samples to detect small effects. And we always have this problem, again, that if we get no effect in an experiment, it may just be that the sample size was too small, rather than it really was that there was no effect. So the power problem remains, but this usually means that before you do an experiment, you'll do a power calculation and calculate how big a sample you will need to get the expected effect. And if you do too small an experiment, you may not get the effect just because it's too small. There are still some problems with experiments. I think they solve a lot of the problems that we talked about. There's a problem of internal versus external validity. And this is really a problem that experiments are very convincing in the setting in which they're conducted. If you're in a different setting, if you're in a different country than the experiment, it's not clear that the thing will work in the same way in your setting. So experiments tend to take place in one setting. And the external validity is how generalizable the results are. And that may be a problem. And we may have to do lots of experiments in different settings to be convinced that the effect is a general effect rather than a real effect, but only in one location. The experiment may not tell you very much about mechanisms. It tells you the experiment has an effect. It doesn't really tell you why. And you may be interested in why. If you're designing a program, it may be that you don't want to do exactly the same program as was in the experiment. But because it doesn't tell you why, you don't know which part of the program or policy was doing the work. And so the experiment doesn't tell us why things happen, it only tells us that things happen. And finally, I think a real issue is feasibility and ethics. Some experiments are simply not feasible, that it's too difficult to do the experiment, and some experiments are unethical, particularly things that would affect people's health, that we think would affect their health in a negative way, may be unethical. And so we may, for these reasons, be restricted to observational data and not be able to do experiments. But I think where experiments are possible, they give us very convincing evidence of an effect in that setting. This again is some work I did in MATLAB in Bangladesh, and this was looking at maternal tetanus vaccination, and this just looks at the mortality effects. So what we see here is there was a randomized controlled trial. Half the women were given cholera toxoid, half tetanus toxoid. And this looks at the mortality in children born afterwards. And the tetanus immunity is passed on in utero to the children. And so what we see is in the control group who got the cholera toxoid, who didn't get the tetanus immunity, we see high levels of mortality from days 3 to about day 12 in that group of children. And these children are acquiring tetanus at birth, usually through infection of the umbilical stump, and that's leading to high levels of mortality after about 3 or 4 days. And that mortality, that tetanus mortality, is not present in the group where their mothers got tetanus toxoid. I think that's very convincing evidence because it's a randomized controlled trial of, I think, 80,000 women. So it's unlikely there's any confounding that there was something else going on in these women because of the randomization. It's not reverse causality, both because of the timing, and there's no way the children could be affecting the randomization. And so I think this is pretty convincing results that the tetanus toxoid is having an effect. What we did is then we wanted to look at the socioeconomic effects of the intervention. And this looks at the effect of on education of children of the treated mothers versus the control mothers. And this is only looking at the group whose parents had no education themselves. So these are women who had no education, and what happened to their children depending on whether they were in the tetanus group, or which is the treatment group, or the control group, which got cholera toxoid. And what we see is that the number of children who had 8 or 9 years of schooling goes up by 3 percentage points, whereas the number of children who had no schooling goes down by 3 percentage points in the treatment group. So the treatment seems to affect not only mortality of children, but also their educational outcomes. But it's affecting the educational outcomes of a very small number of children, but in quite a large way. It's moving them from 0 to 8 years of schooling. So what seems to be going on is some children are acquiring tetanus and dying. Some are acquiring tetanus and being cognitively impaired, which is affecting their schooling and later probably socioeconomic outcomes. So what we've done is address these issues of causality, both in observational data and moving towards experiments. And I think even in observational data now, I think with the matching methods, with the regression discontinuity methods, we're getting quite good ways of estimating causal effects even in observational data. I'd also push you towards natural experiments. Things where we have naturally occurring treatment and control groups that can be analyzed is also giving us convincing evidence. And then best of all, if it can be done, randomized interventions. Accompanying this lecture is 2 homeworks, and those 2 homeworks provide some data. And what people will do in homework 1 is get some data and look at regression analysis and compare that with coarsened exact matching. So we talked about coarsened exact matching and how it worked, and this will go into more detail on how it works and ask people to actually carry it out on a data set. And then in homework 2, we'll look at a policy intervention that occurs at the group level and look at a difference in difference estimate of that policy effect. And then go on to adjust the standard errors for the fact that it's a group intervention rather than an intervention that is occurring at the individual level. And I'll stop there and say thank you very much.